next thing is when you've got sets that sit within other sets. Okay, so here's an example. Yeah, it is. Actually, that's exactly what it is. There's two illustrations here. Okay. Now, you remember we had the U for union, like this, and we had this upside down U for intersection. So now I've got a sideways one. Okay. And what does it mean? Okay. Now, it's a relationship between two sets. Okay. What it means is subset. Okay. So this means that everything that's in A is also in B. Everything that's in A is also in B. Okay, so hold on. I had these two sets before.
Why aren't not being the same?
Ah.
No, the inside.
Hold on. Yeah. Okay, so hold on a second. What did I write? I can't remember now.
2, 3, 5, 7.
It's the primes, isn't it?
Prime.
5, 7. Yeah, that's it. Okay. So, you can see here, right? These two sets overlap, but neither of these sets completely sit within the other one. Okay? So, for instance, if I gave to you, I'm just thinking, I'll give you a boring set. C equals, let's just call it, oh yeah, we'll call C A, B. Okay? So we already defined A intersection B, right? It's just 2. It's just 2. Okay? So if I call that C, then C is a subset of both of these. Everything that's in C is in A, everything that's in C is in B. Right? So I could write this. C, which I'm calling, it's just 2. It's just 2. C is a subset of A. C is also a subset of B. Okay? Yeah, I suppose you could. I don't think it's especially common. I'm just going to leave it as 2 statements though, because it really is 2 statements. Okay. So what's the definition? Every element in A is an element in B. Okay? But as Anish points out, you might get a really boring case of this, right? For instance, suppose I introduce to you set D, right? And I said, let's call D this. Okay. Now, this is an equal set with A, right? Remember, I don't care about order, okay? So, that's a bit weird, but look, you can see that D and A fit this definition, right? Every element in A is in D, right? So A is a subset of D, but D is also a subset of A. That's just a bit weird, right? So what we tend to mean more is this, without the line underneath it. Should I get this right?
A is B.
Okay, so we call this guy the proper subset. Okay, which means that everything is in A is in B, but B's got something else, right? B's got at least one element that isn't in A. Okay. So here's my diagrams now. Okay, I've got, let's go with D and A. Here's D, and here's A inside it, right? And that's 2, 4, and 6. They're subsets of each other. They're mutual subsets, if you like. Okay, but a proper subset, there's going to be something else. Okay? You're talking about
You have D in here.
no, I'm talking about these two, which is still this one. I'm using this symbol. If you like, the way I like to think about it is think about your language for inequalities, which we're a little more familiar with, right? So for instance, if I say A is less than B, right, it means that they can't be the same number, right?
Yeah.
Like if they're both 5, then that's not true. But if I say is less than or equal to B, they can be the same number. So when you see this, it's like A is a subset or it's equal to, right? They can actually be the same set. Whereas here, B has to be bigger. There has to be something in B that's not in A. Okay. So it's this and B has an element not in A. Okay, yeah.
If you want to draw the diagram for A and C, then it would be A with a big circle and C and a small circle.
So let's just quickly draw. What did I say? I need a new set, don't I? I actually can say that C is not just a subset of A. C is a proper subset of A. I can actually say that. Be careful, if you're like me, your C's look like subsets, but anyway. Okay. So that's where I got this. Is that okay? Can you see there are elements in A that aren't in C? Okay. Now we're talking a lot about elements and what belongs to what, okay? So if you take this subset symbol, right, and you introduce a line in the middle, like so, what you get is the Greek letter epsilon. Yep.
Oh, why is there a D?
I introduced the new set. Okay. So if a number A is an element of a big set A, right? Is an element of, right? So you've got an object that belongs to a set. Okay, so for instance, look at the numbers we've got already. I can say 2 is an element of A. Okay, 2 is an element of A. I'm not going to draw a new diagram for that, we've already got enough diagrams. Where you will see this most common is when we say things like this. Okay. You remember I gave you some quadratics before, something like, say this. I'll just think of an example. X squared. Okay, here you go. Here's a quadratic, right? You can say either no real solution. I should write real. Or alternatively, you can say no solution because X belongs to is an element of the real numbers. And you'll see this in textbooks, this kind of language, right? That's the shorthand for real numbers, okay? X is an element of that set. It's a set of all of the real numbers that exist. It's an infinite set, obviously. Okay. All right, how are we going? I need this.
Is that the letter E or something?
It's two things. Number one, it's the union and the intersection symbol sideways and a line. Or alternatively, it's the Greek letter epsilon. It's the capital epsilon. Okay, now I think there's one other important one I want to tell you today.
I like this epsilon.
Yeah. Here's our last important one today before I set you off on a few things. It's the idea of something you're familiar with from probability. Okay? Now, not to be confused with what this means in geometry. In geometry, this means two angles that add up to 90 degrees. Okay? Which, by the way, how much trig have you guys done? Finished? Year 9s, how much trig have you done? Finished? Yeah, so you guys learned about sine and cosine, right? You guys know that the co in cosine stands for complement, right? Yeah? Anyway. Okay.
That just like opened up my mind.
In set theory, come on guys, come on. Sine 20 degrees equals cos 70. Didn't you ever think it was...
Oh my god.
Yeah, I knew that. I never
Okay, anyway.
So much easier.
Refocus.
I know you know what's happening in our math class.
Okay. Now, like I said, different branch of maths. So it's got a different but related meaning. You've actually seen this, like I said, in probability. If I say either, there's lots of different ways to do this. You can see A with a wiggly line with a tilde over the top. you might see A with a dash on it, or you might see A with a C for complement next to it. They all mean the same thing. As a personal preference, I think my personal preference is for this one, okay? Because later on when you learn calculus, this will be one of the shorthands for differentiation. Later on when you learn radian measure, that looks a whole lot like the unit for radians. So that's why I prefer this one.
Isn't radians and pi?
You are confusing what radians are with what pi is. The short answer is no. I can say 2 radians, no problem. It doesn't have to have 5. But anyway, we'll get onto that another time. Now what does a complement mean? Now, this is a bit tricky. What this means is all the elements that are not in A, right? But that then, sorry, not in A. But this then raises a question. For instance, this is A up here, right? 2, 4, and 6. So if I said not A, right? If we're not careful about this, not A will have like, it'll be an infinite set, which will be meaningless, right? It'll be all the numbers except 2, 4, and 6. So what they do is, for each individual situation, where's my black? Where'd it go? This will have to do. They introduced this important set.
Just that we always just.
Okay? So this is a U with an extra line on it. It's what we call the universal set. Now, its name is a bit of a misnomer. The universal set changes for every situation you've got. You define a new universal set. I'll give an example. If we had a die, rolling dice, okay? The universal set would be 1, 2, 3, 4, 5, 6. There are no other meaningful values in that set, right? So if I said, look, A is 2, 4, and 6, I could also say it's all the even numbers on my die, okay? Now, not A has a sensible meaning, right? In this case, not A would be everything in here that isn't 2, 4, and 6. So it'd be 1, 3, and 5. Okay? So in order to define the complement of A, you need to know, well, what's the wider context? Okay? So here's the way that I would draw this. You've got these circles which each represent sets. Around that, you draw a rectangle, the universal set. Okay? So I'm going to call that rectangle U. Okay? And then inside that, right, this is what I call A. Okay? So in this example, you've got 2, 4, and 6 inside A. And then I have 1, 3, and 5 outside A. So I would colour in the outside of A. That's the complement of A. So I should put 1, 3, and 5 in here, shouldn't I? Okay. From Rowan Williams, he gets in your head, doesn't he? So here you go. If I make this the universal set, okay, therefore in this case, not A, the complement of A would be 1, 3, and 5. Okay, make sense?